Welcome to our channel, Code Crusaders. Let's get started and tackle the problem together. That is, House Robber 3. The problem is to find the maximum amount of money that can be robbed from a binary tree without alerting the police. The key constraint is that if two directly linked houses were broken into on the same night, it will automatically contact the police. The problem can be solved using dynamic programming. The basic idea is to recursively calculate the maximum amount of money that can be robbed from the subtrees of the current node. To avoid alerting the police, the thief cannot rob both the current node and its immediate children. Therefore, the maximum amount of money that can be robbed from the current node is the maximum of the following two options. 1. The maximum amount of money that can be robbed from the left subtree plus the maximum amount of money that can be robbed from the right subtree. 2. The value of the current node plus the maximum amount of money that can be robbed from the left subtree's grandchild plus the maximum amount of money that can be robbed from the right subtree's grandchild. To avoid redundant computation, we can use memoization to store the results of subproblems in a lookup table. This way, we can avoid recalculating the same subproblems multiple times. In this code, we use unordered_map lookup to store the results of subproblems and int helper function to calculate the maximum amount of money that can be robbed from the binary tree without alerting the police. In the helper function, it checks if the input node is null. If it is, then it returns 0. If the node is not null, it checks if the result is already in the lookup table. If it is, then it returns the value stored in the lookup table. Then it calculates the maximum amount of money that can be robbed from the left subtree, the maximum amount of money that can be robbed from the right subtree, the maximum amount of money that can be robbed from the left subtree's grandchild, and the maximum amount of money that can be robbed from the right subtree's grandchild. Finally, it calculates the maximum amount of money that can be robbed from the current node by taking the maximum of the two options mentioned above and storing the result in the lookup table and returning the result. This way, the function will return the maximum amount of money. For example, consider the following binary tree. The maximum amount of money that can be robbed is 9. The thief can rob the houses with values 3, 5, and 1 without alerting the police. In this example, the algorithm starts at the root node with value 3, it checks the left subtree and the right subtree. In the left subtree, it finds that the maximum value is 4, and on the right subtree it finds that the maximum value is 5. Since the thief cannot rob both 3 and 4, it takes the maximum of 4 and 5, which is 5, and adds it to the root node value 3. Then it compares that value with the second option, which is robbing the current node and its grandchild. It finds out that the second option is not better than the first one, so it returns 8 as the result. The time complexity of this problem is big O(n), where n is the number of nodes in the binary tree. The reason for this is that the algorithm visits each node in the binary tree exactly once. At each node, it calculates the maximum amount of money that can be robbed from its subtrees. These calculations are done recursively, and each calculation takes constant time. Therefore, the total time complexity of the algorithm is big O(n), where n is the number of nodes in the binary tree. The space complexity of this problem is big O(n). The reason for this is that the algorithm uses a lookup table to store the results of subproblems. The size of the lookup table is equal to the number of nodes in the binary tree, which is n. Since each node is visited exactly once, the space complexity of the algorithm is big O(n). It is worth noting that the space complexity could be reduced to big O(h), where h is the height of the tree, as the maximum number of elements in the stack would be the height of the tree. However, in the worst-case scenario, the height of the tree is n, so the space complexity would be big O(n). Overall time complexity, big O(n). Overall space complexity, big O(n), where n is the number of nodes in the binary tree. Thanks for following along. I appreciate your attention, and I hope you found this explanation helpful. If you found this video helpful, make sure to hit the like button, leave a comment, and subscribe for more content like this.